All right, so we left off last class. We were in Excel, so we're going to kind of pick up where we left off, finish up the Excel example. This will kind of help with that second Excel assignment that's up on Canvas right now. It's basically building your own contingency table and then using that table to answer some questions. So I'll kind of add in some questions, that we could answer using this contingency table as we go along. So just to kind of refresh what we were doing, right? We're looking at these contingency tables. We always thought about like event A and its complement and event B and its complement. So here our events were, does the industry have 10% or higher union membership, or is it below that? And then is the industry have a wage differential of $100 or more between union and non-union workers, or does it have a less than $100 differential? So the idea behind this was, maybe industries that have a higher percentage of union workers are able to kind of bargain their wages even higher, and it's more likely then they get this huge wage differential from their kind of non-union counterparts. Right? So we use this Countifs formula, right, where we first selected that variable of union membership and said we want to count it if it's greater than or equal to this cutoff value of 10% that we chose. Then comma, go through the difference in earnings variable and only count the observation if it also has a difference in earnings that is greater than or equal to the $100 cutoff that we set. So that's what we kind of ended last class, kind of building that Countifs formula. And what this should do is give me the number of industries in this data set that have 10% union membership or higher and a wage differential of $100 or more, right, between those union and non-union workers. So we get that there's 221 of them. Right? Well, I basically want to go through this process and find the other three different combinations, right? Does the industry have below 10% union membership and $100 more wage differential, below 10% and less than $100, above 10% and less than, right? So I want to count up the number of industries that fit those categories. So I could type this Countifs formula in 3 different times. Probably an easier way to do that is if I just highlight this formula, so I'm in the cell so I can see the formula, and then I copy it, then I'm going to hit enter. That's just an easy way to get out of the cell. If I then click on the cell I want to paste it in, if I copy and paste this way and don't just drag the cell, it doesn't update any of the cell references. So usually we like freeze them. That's probably better practice to freeze our cell references, but you can copy paste kind of the formula in this, this manner as well. And now notice everything that we had before is exactly what we want now, except for now, when we go through, we want to count it if it's not greater than or equal to 10%, but we only want to count it if it's that union membership value is less than the 10% cutoff. But then we still want to count it if it's less than 10% and a wage differential of $100 or more, or greater than or equal to $100. So probably a better way to do that than copy and pasting, a little bit quicker. If I highlight my references, hit F4 or Command T on a Mac, F4, Command T on a Mac, just freeze everything. I can copy it over and down and notice nothing changes. So I should keep getting, I gotta move this out of the way here. Nothing changes, so I keep getting that same frequency. And then I just need to go in, okay, this category, I need to count if it was less than that 10%, and then greater than or equal to that $100 wage difference. Down here, it's gonna be less than 10% and also less than $100 wage differential. So basically, once I copy it down, I'm just going through and making sure these equality or inequalities match up with the row and column heading. So this one, greater than or equal to that 10%, wage differential of, okay, I gotta change this one. This would be less than 100. So once you've typed it in once, if we just freeze all those references, copy it over and down, then it's just a matter of going in and updating those kind of inequalities or these equality operators in the Countifs, right? To make sure that I'm counting whatever the row and column heading, right? I'm following the criteria of my row and column headings. Okay. Any questions on any of that? You want to see something again? Yeah.
Well, this example that you're doing currently,
Mhm.
be up on your YouTube.
Yeah, so I'll put this up on, actually, I'll probably cut out what we did last class and today, and then splice it together and just upload today's lecture, but also one just Excel video. Any other questions on anything I just worked through here? So one thing we'll have to be careful of when we're doing this is, right, if we think of these general contingency tables, we always had A and A complement. So in practice, where that gets a little tricky is with your equalities. Notice if I, let's say I had changed the sign here to be less than, but I left equalities on there. So like maybe here, oops, I leave my equality on there. It changes my values a little bit, right? Because I'm capturing potentially some observations that are in both categories. Right? I need to make sure that that equality is only on one, right? Because this should be event A and its complement. So I can't have any observation that's going to be in both of them. Right? So I'm going to undo those changes. You can kind of see it change my numbers a little bit there. Oh, I think I went too many, didn't I? This should be above 10% and less than. There you go. So at this point, right, it's very similar to what we were doing when we had probabilities. So we still have frequencies. We'll eventually turn those into probabilities in a second. But to reproduce these total columns, I'm just going to add across the rows. So I'm going to use that sum function. I could just, click equals this plus this, but sum function is kind of easy. So I'll highlight those numbers I want to add across the rows. Then when I copy this down, K9, L9 become K10, L10. So that's what I want here. And then I'll add down the columns, similar to the idea of what we were doing with contingency tables. Oops. So I'm just using that sum function once again, adding down the columns. Now, the reason this works, if you think about it, there's 221 industries with a wage differential of $100 more and 10% or higher union membership. There's 184 that have a wage differential of $100 or more and are below 10%. Well, if I add those together, that's just every single possible industry that has a $100 or more wage differential, right? So there's 405 of those. Okay. If I look at all the industries that have $100 or more wage differential and all those that have less than 100, that's every single possible industry in my data set. So if I add my totals up, what should this value represent? This would be the total, right? If I think about, I'm looking at all industries that have a $100 wage differential or more. There's 405 of them in my data. And then the industries that have less than $100 are 330 of those. So if I add those together, that just represents, total number of observations in my data set. So one way I can check here to make sure that I've done this correctly is, once I add these totals, I should be getting the total number of observations in my data set. We said we can check that using the count function, right? We use that count function and then just select, we'll select that first variable, hit enter to go back up to the top of that cell. Notice that count function tells me, sure enough, there are 735 observations. If I had made an equality error, like let's say I left the equality on here, notice, okay, I'm off by one, I did something wrong. I go back in here, oh, okay, sure enough, this was supposed to be just less than 10%, right? So I had a mistake. Oh, okay, now I've got my total number of observations kind of correct, okay? Any questions on that? So once we use that count ifs in those top 4 left cells, right? That's kind of counting the number of observations that meet this criteria and this criteria, right? Those represent intersections. Our totals represent the sums of some of those kind of 2 intersections, where we said that kind of the total number of industries that fit the row or that fit the column heading. Right? So to turn these into a contingency table, to turn these into probabilities, what might I do? If there's 221 industries that fit this criteria out of 735, how could I turn that frequency into a probability? Just take 221 and divide it by total number of observations, right? So 221 divided by that total number of observations, 735. And that turns it into a probability, right? If I select an industry at random, the probability that it fits this criteria, well, there's 221 out of 735. So that's the probability that it's one of those industries. Now I could do this for every single frequency, turn them all into probabilities by simply dividing by the total number of observations. But notice, so I copy this over. Oh, what's going on here? Oh, well, it's updating kind of everything. Oh, actually, this one, I went too far, didn't I? It's updating my total number of observations cell reference. So I want to go back in and I want to make sure that I freeze that, right? I always want to divide by the total number of observations. When I copy this over and down, I just want it to match up these frequencies. Okay. So now when I copy this over and then down, now I get everything kind of operating correctly. And hopefully when I get to this total column, right, I should just be taking the total number of observations, dividing it by the total number of observations. So I should be getting a 1 here, right? It's another kind of place where we can kind of check to make sure what we've done is looking correct, okay? Any questions on? In practice, one thing I just wanted to mention, because I don't remember if I did last class. Let's say I built this table and I got my frequencies and now I want to turn them into probabilities. If I just highlight that, copy it, and then, so I won't use the shortcuts because you can't see them. So copy, paste, right? And then just delete these. I kind of have like another table set up that I could then find the probabilities of. That's just an easy way so I don't have to retype all those labels in. But once I have these probabilities, I can start to answer questions about conditional probabilities, intersections, unions. So down here, scroll over a little bit, I've got a couple things that we could find, right? Maybe I ask you for what the probability that if I select an industry at random, what's the probability that has union membership above 10% or 10% or above, right? Well, that should just be the 10% or above. Go down to the total, 0.39. Right? So I can just click on the value, hit enter, and it spits that value in there for me. Maybe I want the probability of being 10% or higher and a wage difference of $100 or more. Well, that's an intersection. So one of those top 4 left cells, I'm just going to match it up, 10% or higher, wage differential of $100 or more. That's right there, right? So it's just like what we were doing by hand, but you've got a table in Excel now, so all you have to do is click on the values. If I want to find a conditional probability, remember we said that's the same thing as the intersection of those 2 events divided by the probability. I'll change this to make it a little bit, there you go. The probability of the intersection of those 2 events divided by the probability of whatever we conditioned on. That was kind of our multiplication rule. We used this last class. We'll kind of use it again today, even after we get out of Excel. But that's the general form. So if I want the probability of seeing a wage differential of $100 or more, given that the industry has a high unionized, is a highly unionized industry, 10% union membership or higher, I could find the intersection of those 2 events and divide by, well, what am I conditioning on? Maybe it makes it a little bit easier if I make it so it's all in one line, right? Okay, I'm conditioning on is it 10% or higher, so I'll divide by the probability of being 10% or higher. So the intersection of these 2 events is right here, divided by the probability of what I'm conditioning on, which is that it's 10% or higher. So I go down to that total, right? And that would be the probability of what I'm conditioning on. All right, so to find these conditional probabilities, we have the information we need in the contingency table. It's just not directly ready for us, right? We have to take 2 of the components in that table, divide one by the other. And really the idea here is that, the entire experimental outcome space of 1, industries that are 10% or higher are really only about 39% of that, or 0.39 in terms of a probability. So we've kind of limited our space down quite a bit. And if you notice, now that, if we want to think about probabilities, there's always, like, we just turn frequencies into probabilities. So we could always just multiply everything by the total number of observations and just deal with the frequencies. So you might think about it as like, once I tell you that to condition on that it's 10% or higher, you know there's only 288 of the 735 industries left. Of those 288, 221 of them have this high wage difference, and only 67 have a small wage differential, right? So the probability, if I know that it's an industry that has 10% or higher union membership, the probability it belongs to this high wage differential category is pretty significant, right? 221 out of the 288, okay? And that's really all I'm doing here. It's just that I'm using the probabilities, and every probability is being divided by the total number of observations. So it really doesn't change anything, right? If I divide everything by the same number, the relative size or the ratios don't change, right? But it might be easier to think about it in terms of kind of the frequencies as well, right? Probabilities behind the scenes, there's always frequencies that are kind of hidden in those probabilities. Okay? Any questions over anything there? Okay. Then I've got kind of another one, what if I had a high wage differential given that the industry is below 10% union membership? Well, same idea. I'll find the intersection of those two things. So that is right here. Divide it now by what I've conditioned on is that it's below 10%. So I know that there's only 60% of the industries left once I condition on that, right? And then it's just, kind of same process, but I can find the conditional probability there. And the reason why these conditional probabilities are interesting is it kind of tells us something about the relationship between these two events, right? Notice if I'm looking at an industry with high union membership, right, given that it has high union membership, the probability that that union can get wages to be $100 above their non-union counterparts, about a 76% chance here, right? Or the probability of 0.67, 76, right? However, if I'm looking at an industry that is below this kind of 10% union membership or low unionized kind of industries, the probability that those unions can get $100 or more wage differential from their non-union counterparts, only about a 40% chance, right? Or probably a 0.4. So kind of being in these highly unionized industries, it kind of almost doubles that impact. Right? Questions on anything related to the Excel? I'll probably kind of leave it there, and we'll kind of jump into the next topic here. But this is how we build our own contingency table from, right? We just started with a data set, right? And we're just defining the events we're interested in. We can calculate the frequencies for the different combinations of those events and their complements. We can then turn those into probabilities and then kind of answer different questions, okay? So this is basically what the main part of the Excel is going to be. It's going to be building a contingency table. And then I'll ask you some questions like this. You could do them by hand, but because it's an Excel assignment, I want to see you use Excel to answer those questions. So even if it's something as simple as what's the probability of this event, put this into Excel, kind of get used to, okay, I can just click on the value in that contingency table as opposed to writing it out, typing things into my calculator, to find these conditional probabilities. So all your work, even for these ones that kind of seem like you could do them by hand, on those Excel assignments, I'm expecting that you do all the work in Excel, right? And so I think on the when I posted, I even said full credit is only given to for all work done in Excel. Okay, it's a little bit lenient on that first one as I'm kind of going through and grading those, but here on out, I need to see all of your work in Excel. That's the purpose of the Excel assignments, right? No questions. We're okay with kind of leaving this here. So, we just worked through everything, but the file's up there. It kind of has all of our work on this completed version. I also put up another file called probability tables. It's just another example if you want to take a look at it. I thought it was interesting at one point, and then I don't know, became less interesting to me. So here I kind of define some things as using this ASVAB score, which is kind of like an SAT or an ACT, like it's a standardized test. So to some degree, the military uses it. but it measures like aptitude or skill or kind of intellectual ability, among other things. But it's some measure of kind of ability. And then kind of I had some drug use variables that I kind of looked at, kind of built these contingency tables, and you can think about using these to find different probabilities. But just another example of using that count ifs, right? And then turning those into probabilities. So that's up there on Excel as well. We're not going to work through it in class, but I had it laying around, so I figured I'd just throw up a second example just in case. Okay. And it's pretty obviously named probability tables. So if it's another example of that. We'll come back and I'll end with this. Here's just kind of a summary of our rules. So let's go to kind of the next topic that we're going to cover. Right? So we're going to kind of heavily rely on this idea of using the multiplication rule. So being able to calculate intersections using conditional probabilities and whatever we're conditioning on. So Bayes' theorem, the general idea, and don't waste too much time with this, but it's been started with this theorem. It's now like there's Bayesian statistics, right? There's like graduate level Bayesian statistics where it becomes like basically computer programming and data generation, and it's a whole thing. But the basic idea of all of it is that we start with the probability of some event, right? We run this experiment. Given the information we see or the outcome we see for that experiment, we update our probability of the event occurring, right? For instance, if I think that something's impossible, right? Maybe I say, okay, what's the probability someone's born with, I don't know, purple eyes or something? Right? Well, the probability is 0, right? Well, then some genetic, adaptation happens, and I see a child born, right? I'm looking at birth and recording eye color. That's my experiment. And I record a birth where someone has purple eyes, right? Well, now I have to update my probability, right? The realization of an outcome of that experiment has kind of told me, well, the probability is no longer 0. So that's the basic idea of what we're doing. So the setup of how we're going to be able to use Bayes' theorem has to do with situations where we've got two states of nature, right? And those states of nature are complements. Okay? So this might be something like someone is either guilty or non-guilty of a crime. Someone either is HIV positive or HIV negative, you're either pregnant or you're not, right? We go through these scenarios where there are only two real states of nature. Okay? So, you either, even if it's not that the jury finds you guilty or not guilty, it's that you either committed the crime or you didn't, right? It's one or the other. So we've got these two states of nature, and they're basically complements of each other. If I take the probability of each state and add it up, what should I get? Probability that someone's HIV positive plus the probability someone's HIV negative. That's every single person. So those probabilities should add up to 1, right? We've got our states of nature have to add up to 1. Okay? And we could complicate this with multiple states of nature, but for us, we're just going to stick with 2 to make it easy. We're then going to be interested, okay, what is the true state of nature? But I never truly know, right? Especially when we think about it in the context of the crime example. I don't truly know if someone's guilty or not, unless I have video evidence. Maybe I'm just like hearing the story, right? Of did they do this or did not? He said, she said. And we can run some tests to get a better idea, right? So this makes a lot of sense in kind of the medical examples, right? If someone has this disease or not, we don't actually know looking at them. Like I'm not aware of people that can like see, into your blood that this disease exists, right? So we run some tests, right? Then based off the outcomes of those tests, we update our probabilities about whether or not you have the disease, okay? So the outcomes of the test, we're going to, for now, assume that there's no inconclusive test, that like if there was, we just run this test until the first time we get an outcome, right? So inconclusive is like if that happened, we just run it again until we get an outcome for the experiment where we get either a positive or a negative test result. Or think about in the concept of like the jury either finds you guilty or not guilty. It's a hung jury, you go through the jury process again until you get that outcome. Right? So usually we'll think about these as positive and not positive, or positive and negative. I said from the last slide here, ignore that. I moved things around. We might be interested in something like, okay, given that I see a certain outcome on the test, what's the probability that this state of nature is the true state of nature? So here I might be something like, given that, HIV test comes back positive, what's the probability the person actually has the disease? Because we know that these tests aren't 100% accurate, right? If they're 100% accurate, then none of this really matters. Right? So that's the question we're going to eventually build to. But to get there, I'm going to have to introduce Bayes' theorem or Bayes' equation, and where it comes from, trying to give some justification. So we wanted this conditional probability, right? We saw some outcome of the test. What's the probability of this certain state of nature? Well, we can break that down to the intersection of two events divided by the probability of what I'm conditioning on. The problem is here, if I'm thinking about E, this outcome of the test is that the test comes back positive, then the probability of E is really, we're saying, the probability that the test comes back positive. Right? So that denominator up there, the probability of E, the probability the test comes back positive, I don't really know, right? Based off like the manufacturers and things of these tests, I know the rates of false positives, right? That you'll get a positive result given that you don't have a disease. And I might know the probability to accurately identify someone. So given that you have a disease, what's the probability the test can identify it? But I don't just know for the general population without any more information about them. Well, what's the probability you just get a positive test result? So I'm going to have to break this down. So the first thing we're going to do is recall that using that multiplication rule, I can rewrite the intersection of two events as the conditional probability and then multiply by whatever I'm conditioning on. Well, that doesn't really help me. I just said I don't know what the probability of E is. But remember, order doesn't matter. So I might initially try writing that intersection out like that, but the probability of what? S1 given E is the same as E and F, or sorry, the probability of S1 and E is the same as E and S1, right? So now if I use this form and I try to rewrite it, right? Okay, I can write it as this conditional probability times what I'm conditioning on, right? Because the order here didn't matter in my intersection. So we can use that, right? And plug this guy in here to the numerator. Yeah. Positive. Yeah, if you want to write in, if you don't like my shorthand, you could do this, right? It's positive. No, I don't mean like you specifically. I mean, if it's easier for you to think about, right? If I ever write something up here, you're just like, why the hell did you choose that thing to represent that? If you want to write it out, whatever makes the most sense to you, like by all means do it. Right? Sometimes I don't even understand why I didn't choose the shorthand. So yeah, so positive, right? You could write the word out. Honestly, when it gets closer to the exam, that's actually like a decent point. Is like when you're writing things out in the context of whatever your example is, like choose the thing that makes the most sense to you. And if it's writing out the entire word, that's fine, right? I mean, that's whatever way you can sort out the best. So we've got this numerator. We can then break the denominator down in a little bit here. So the probability I see a positive test result is made up of two groups of people. People who have the disease and see a positive test result, and then people who don't have the disease but got this false positive, right? They have the positive test result. Okay. So we know that the number of, if I gave everyone in the US, an HIV test, right? I'm going to get back a bunch of positives. Some of them will be individuals who have the disease. Some of them won't, right? Some of them will be those false positives. So now that I've broken that group up into these kind of two separate groups, now it's just using this definition, right? I can rewrite these intersections using conditional probabilities times what I condition on. Now I've got something I can plug into the denominator, right? I tried to color code this, and I think there's another, I think we did it right. I have another slide where my box is moved. This green box should be up here, so I'll move it, and then I'll move the other one. Later on, you'll see like the box is supposed to be pointing at something that's like way out here, so I don't know why. But basically, all we're doing is using that multiplication rule to substitute things in, and it looks like, okay, why are we making this what looks like a simple equation much more complicated? And it's because a lot of times when we have an example like this, where we want to know the state of nature and all we have is the outcome of the test, generally, we only have like these conditional probabilities. So I'll walk us through an example, we can kind of see what this looks like. Before I do that, where are we at in time? Oh, perfect. So we already talked about this rule, right? The two states of nature, we know the probabilities have to add up to 1, right? We actually have another thing that we know, which is that if I condition on the same state of nature, so I didn't say which one here, SI, could be the first state of nature, it could be the second. But as long as I'm conditioning on the same state of nature, those conditional probabilities for the outcomes of the two outcomes of the test have to add up to 1. What this is really saying is like, if I say, okay, given I'm looking at only individuals who are HIV positive, right? I'm conditioning on the same state of nature. I know for those HIV positive individuals, they either get a positive test result or they get a negative test result. So for someone who has HIV, if they take an HIV test, the probability they see a positive test result might be 0.9, which means given that they have HIV, the probability they see a negative test result would be 0.1. Right? There's only 2 outcomes of the test you can see. So as long as you're conditioning on the same state of nature, right, you're looking at the same individual, either HIV positive or HIV negative, the outcomes, the probability for the outcome of the 2 tests have to add up to 1. We'll kind of exploit this and I'll show you why this helps us out. If we condition on different states of nature and try to add up conditional probabilities, who knows what that is? It could actually be over 1. Doesn't have to follow any rule, right? So let's kind of jump this HIV test example that I don't know. I use this one because I think it's easy to think about disease. I guess we could use COVID here, but I've got old numbers and I hate talking. I don't know. I use examples because it's relevant, but I'm very tired of talking about COVID. So, all right, maybe we have something like this. We're first told, all right, based off historical data, right? I know that the probability that someone chosen at random in the US, the probability they have HIV is 0.006. So roughly 0.5% of the population. And I tried to use, I looked these up, CDC, and then I forget what manufacturer of HIV tests I looked up to get some of these numbers. And then I rounded them basically. So we've got the probability someone's HIV positive, and kind of think about this as my first state of nature. So if I think about my other state of nature, S2, someone being HIV negative, what should that probability be? Either have the disease or I don't. So if the probability I have the disease is 0.006, the probability I don't is, yeah, right, 1 minus 0.006 or 0.994. So writing it out this way, if you're given the probability of one state of nature, because you know that the probability of both states of nature have to add up to 1, you automatically are like indirectly being given the other one as well. Any questions on that? It's not too bad. Here it's a little bit trickier. And I generally would phrase these a little bit different. So generally, the way I would phrase this, and I'm just writing this out the way that I kind of saw it on the website, where they gave their test accuracy rates. But I probably would say something more like, given that someone is HIV positive, the probability the test comes back positive is 0.999. Using this terminology of given, that tells you, oh, I'm looking at a conditional probability. What am I conditioning on? What's given to be true? Well, that the individual is HIV positive, right? So given that the individual is HIV positive, the probability that I see a positive test result is 0.999. So I think on the slides, I use this, right? So P0S or positive sign, right? So this is told to us to be 0.999. This test is very good at accurately identifying an individual with HIV, right? If they actually have it. Well, notice this is like my state of nature, and this is the outcome of the test. So I automatically know that if I condition on that same state of nature, right, I am looking at individuals who are HIV positive, the probability that the test, not that it comes back positive, but that it comes back negative, right, would have to be what? So for the same type of individual, in terms of this example, there's 2 outcomes of the test, so this has to be, yeah, I heard someone say it, 0.001, right? Because we know if we condition on the same state of nature and add up those probabilities of both outcomes of the test, those have to add up to 1. Those are the only 2 outcomes that we can see. Any questions on this? The next thing we're told is the probability that we see a positive test result for an individual who's HIV negative. So now that we're looking at people who are HIV negative, we would say, given that someone's HIV negative, probability that we see a positive test result is what? 0.01. So it's kind of like the false positive rate, right? For individuals who don't have the disease, right, conditioning on that, the probability they get a positive test result is 0.01. And if we know that one, also, I don't know how simple, I almost have to put down here something. So we looked at, I'll get out of the way here in a second. Right? The other outcome of the test for these individuals, right? We're still conditioning on their HIV negative. We know these 2 have to add up to 1, so this would be 0.99. So we're really only directly given 3 probabilities here. 2 conditionals, and then kind of 1 probability of the state of nature. But because of these rules we had, right, we know if we're given 3, we can come up with 3 other ones. Every probability we're given has a counterpart. Now, we might not need some of these probabilities, but if we ever do, we've got them here. Okay? So you can also set this up as a tree. For some people, this makes a little bit more sense to. For me, just like writing the probability down and knowing, okay, there's a counterpart that adds up to 1, doing that makes sense. But it's also a little bit easier to keep track of if you think about, okay, there's 2 outcomes of, I could have for the state of nature. Okay? So they're on the same row, so I know those have to add up to 1, right? Probably someone's HIV negative plus the probability someone's HIV positive. That's every single person. Those have to add up to 1. I then have like 2 branches. So here's my HIV positive branch. So I'm going to always on this second row, right, on the HIV positive branch, condition on that state of nature. Right, so I'm conditioned on the person who's HIV positive. I'm then looking for that conditional probability for the 2 different outcomes of the test. I know that on this branch, on this row, these 2 have to add to 1. I then look over here in this branch. This is the HIV negative branch. So I condition on if the person is HIV negative. And then I know the probability of the 2 outcomes of the test here have to add up to 1. So this is a different visualization of basically what we've just done, right? But I think for some people, this you can organize helps you organize what you're looking for a little bit easier. Okay? Questions on this? Nothing terribly new here. So now that we have these probabilities, how do we actually use that Bayes equation? Okay. Well, we write down all the probabilities that we were given, either directly or kind of indirectly, right? We're given these 2 conditional probabilities. These will be, from those we found 2 other ones up here on the board. But for now, we'll say that we didn't do that and we were just using what we were given. Well, if I'm looking for the probability that someone is HIV positive, given that they got a positive test result, right? So given that they saw a positive test result, what's the probability they're HIV positive? So I think this is probably the easiest way to do this. If I go back, and look at its general form of the equation. So I was looking for, given that the test came back positive, what's the probability that the person was HIV positive? Well, if this is my outcome of the test, and this is my state of nature 1, we'll call it, I could try to write this out, and I might think, okay, I can solve for this using that multiplication rule that I just take the intersection of the 2 events, divide by the probability of what I'm conditioning on. What's the problem with this? This is the whole reason why we had kind of introduced Bayes equation, because we don't have these. We don't have either of those probabilities. So we're going to have to kind of rearrange them, plug in some other equations for them until we get to Bayes' equation, right? So the probably easiest way to do this, we can't solve it kind of using that whole just multiplication. Well, I need Bayes' equation here. But I'm just going to write it out in the context of my example. So I've got my state of nature and my outcome of the test. So when it gets like the exam or something, you'll have this on a formula sheet, right? So I'm just going to start writing out in the context of my example. So the probability of what's in that numerator, S1, my state of nature is that the person's HIV positive, times the probability of what? E given S1. Well, my E is that the test comes back positive, given that state of nature, which is that the person actually is HIV positive. All I did was write that out in the context of my example. Now, one thing you'll notice is the first part of the denominator is the exact same as the numerator, right? Because ultimately what we're doing here is saying, look, I have a group of individuals with a positive test result. These represent people who have a positive test result and have a disease. This group is the number of people who got a positive test result and don't have a disease. So my denominator is like the total number of people who got a positive test result. Now, out of those people, this numerator, right, represents the individuals who got a positive test result and have a disease. So it's like take the number of people who got a positive test result and have a disease divided by the total number of people who see a positive test result. So that first part of the denominator will always be the same as our numerator. So instead of writing that down again, I'm just gonna, it's the same as the top because I don't want to run out of room. It's pretty easy to write. If you're taking notes, just kind of basically write down here. First thing that done. The next thing is the probability of S2, which is the probability that someone is what? HIV negative, like the other state of nature here, times the probability of E. Well, our outcome of the test we're interested in is still that they got a positive test result, given S2, which is that they're HIV negative. Now, once I have this written out in the context of my example, what's the probability someone's HIV positive? I look over on the other side of the board, 0.006, plug in the denominator at 0.006 as well. Given that they're HIV positive, what's the probability they get a positive test result? I think it's 0.99 over there, or 999. So 0.999, 0.999. What's the probability they're HIV negative? We found that to be 0.994. Given that they're HIV negative, what's the probability they get a positive test result? We were told that false positive rate is what? 0.01. Once we plug all those values in, it's just a matter of getting it entered into our calculator, right? So I think I have this on a slide here. There we go. All right, write out the formula in the context of our example, and then just start plugging in the probabilities we know, right? And we just said we have all of it, right? So once I plug all those numbers in, right, I can calculate that conditional probability. Any questions over kind of that process? Or we'll definitely probably go through some more examples on Monday. But I think this is interesting to point out here, right? We got a very counterintuitive result. So given that you see a positive test result, let's say we gave every single person in the US an HIV test, right? Given that someone got a positive test result, the probability that they actually have HIV is only about 38%. Right? So why is that the case, right? If someone's just like, yeah, I have a positive test result, the probability they actually have disease is only about 0.38. So I'll try to kind of do that, why that is, and why that counterintuitive result is actually correct. Okay? So thinking about what these numbers represent, so we can always think about probabilities. Behind the scenes, there's a frequency somewhere. So it's like the number of people in that group. So that numerator represented what? People who had HIV, right? The likelihood they had HIV was 0.006. And then of those people, the people who got a positive test result were only the ones for which the test accurately worked, right? 99.9% of the time. So it's almost like that numerator. If we use like the US population of roughly, I'll use 300 million just to make it a little bit easier to think about. I know it's a little bit higher, but it's about 300 million, right? So if about 0.5% of people, right, 0.006, have HIV in the US, right? We would say that's about what? That's 1%. 0.5% would be about 1.5 million. And of those 1.5 million, we've almost identified all of them accurately with this test of having HIV, right? 99.9% of the time. So as a rough estimate, we'll say there's about 1.5 million people who have HIV, and if we all took a test, they would end up with a positive test result. The other group of people, well, this was kind of like, they had a positive test result and they were HIV positive. So they're kind of one group of individuals who get a positive test result. The other group is people who don't have the disease, 99.4% of people. So roughly, right, if you're doing 300 million, so roughly 297 million people won't have HIV. Of those 297, 1% of them get a false positive. Well, 1% of 297 million is 2.97 million. So even if we just kind of round that a little bit, we've got about 3 million people who are going to see a positive test result. However, they're HIV negative. So the reason why this probability ends up being like 0.38 or 38%, right? It seems counterintuitive, is because even though we're accurately identifying everybody who has HIV with our test, even if our false positive rate is low, it's only 1% here, there's just so many more people who are HIV negative, right? The probability of that second state of nature is 0.994. Right? So there'll be 1.5 million people that get a positive test result and have the disease out of the total of 4.5 million people who have a positive test result. Right? So this group ends up being just more people, because even though the false positive rate is low, there's just so many more people that are HIV negative. 1% of a really large number is going to be greater than 0.999, 99.9% of a really small number of individuals who had it. So, a lot of times this Bayes equation produces a lot of these counterintuitive results, because if the probabilities of those states of nature are pretty heavily skewed, you can end up with a situation like this, where our false positives basically just start to overpower, right, our accurate positives, our positive. So you can go through very similar things like with anything where you do massive amounts of testing, where one of the states of nature has a relatively small probability. Okay. Well, I'll get that Excel stuff up this afternoon as a separate video. On Monday, we'll kind of pick up with Bayes' theorem. We'll finish out material next week. I'll put an announcement up. I think I mentioned last class, that exam I'm going to kind of push forward or like into the future a whole week. So it'll be October 1st in class instead of September 24th or whatever. All right. So enjoy your weekend, and I will see you guys on Monday.